Sine x plus cos x, right? This looks a little familiar to me, right? I've been adding trig functions as part of what we've been doing under identities, right? For instance, if I told you this, sine of a plus b, sine of a plus b, right? We learned an identity for this quite early on, actually. What was our identity for this thing? Sine a cos b, cos b, plus cos a sine b. Good. Okay, right? Now, what I've got here bears some resemblance to this, doesn't it? Right? I've got a sine and a cos, but then there are these kind of other guys floating around. So what do I do with them? Okay? Well, that extra angle is this. Right? How is it that you actually change the phase of a trig function? Suppose I wanted to take like just regular old sine x, and I wanted to move it, say, oh, I don't know, 90 degrees to the right. What would I do? To the right, how would I have to change this function in here? I'd have to go y equals sine of x minus 90 degrees, right? X minus 90. That would change the phase, wouldn't it? Okay. Or if I wanted to move it to the left, I'd say x plus 90, right? So here's what I'm putting across to you, right? This thing here is another wave function. It's like a sine or a cosine, right? But its amplitude has changed and its phase has changed, right? So here's what I'm going to suggest. That sine x plus cos x, the sum of two wave functions, should be equivalent to, that's an identity, by the way. It's not just at certain values. I mean at all values all the way across, right? It should be equivalent to a sine function, another wave function, with a different amplitude and a different phase. Okay?
I forgot how to do it then. I remember.
So, let me just say that again. Let me say that again. Because this is the crucial idea, and the rest of it's just algebra and identities, right? I'm putting across to you, and I hope I made enough of a visual argument, that the sum of two wave functions is equivalent to, not just equal to, it's exactly the same at all points along as some other wave function with a different amplitude and a different phase. Okay, it's been moved around somehow. Okay? Now, this thing is called, it's named after that phase, right? This angle here, right? It's like x and a little bit of an angle, like an angle on the side. And a phrase for on the side, or a word I should say, is called auxiliary angle, right? Auxiliary means it's like extra, right? It's like a little bit that I've added on, right? When when something says, oh, we need to go to auxiliary power, it's like your main thing is shut down and you got to use like the battery on the side, right? It's literally the main angle plus a little bit. That's all it means. Okay? So this idea is called auxiliary angle. Auxiliary angle. Yes.
Those three lines does that represent a new function?
So what do three lines mean, people? We've looked at this before. We used it in the context of triangles. We said it's congruence. In the context of trig, what does it mean? It means equal and always equal to for every value of x. Right? So here's what we're going to do. Get ready, we're going to pull together a lot of things that you've been looking at over the last couple of weeks, and this is kind of like the conclusion of it, right? So, just off of this line, right? This line here, I know what this is equal to. I know what this is equal to, right? It's just an expansion, right? So I've got R outside of, okay, now this is sine A cos B, cos A sine B, right? So let's do it. Sine X cos alpha, cos X sine alpha. You okay with that? Okay, so far so good. Now, keep in mind, alpha is equal to something. It's not a variable, right? I really should have said, alpha is a number, right? It's a real number of some kind. We'll find out what it is soon. But it's completely different to x. Yes, it's another pronumeral, but it has a value. Like it's not whatever I want to be. It's this distance here, and I'm going to find out what it is. Okay? So that's what I have on the right-hand side. Over here on the left, I still have this guy. Hasn't changed. Okay. Now look with me, right? Do you see on the left-hand side, I have a sine term, and on the right-hand side, I also have a sine term. And on the left-hand side, I have a cosine term. And on the right-hand side, I also have a cosine term. Okay? So these guys inform each other, right? Remember, I'm saying this is exactly the same as this, just written in another way. Okay? So I'm going to expand and show you what this is equal to. This thing here is actually, it's shorthand. It's 1 sine x plus 1 cos x. You're thinking, why am I adding the 1 in? Well, you'll see in a second. Okay. When I expand this out, I'm going to expand it in such a way to make the sine x term really obvious and the cosine x term really obvious. I'm going to expand, yeah? So I've got r cos alpha, and then I've got sine x. Do you agree with that? That's just me. I've just slightly reordered it. Yeah.
Is it just a regular R?
Yeah, it's just a regular. It's not an r for real numbers. Okay. That's what I've done with the first term. I'll expand the next one. R sine alpha, and then there's that cos x hanging out on the side. Okay. Can you see why I have written in this kind of unusual? Why have I got brackets way? Okay. Because this one, right, this coefficient of the sine x is that coefficient of the sine x. It's just written in a different way. Okay. So r cos alpha, which is just a number, it's 1. And in the same way, in this particular example, r sine alpha is also equal to 1. Okay? And then my sine x's and my cos x's, they just hang off on the side. Okay? So I would say, and you don't have to write this every time, but this is the first time, so let's make sure we understand what's going on. By equating coefficients, that's what we're doing, right? The coefficient of sine x on the left-hand side and the coefficient of sine x on the right-hand side. They're meant to be the same. They're equivalent, right? So we equate them. We would say r cos alpha equals 1 in this particular case. And r sine alpha is also equal to 1. I just chose a really simple example for you. Okay. Good, sir.
I said
Who you after?
Mark Lane and Aaron Kane.
Yeah, do you need to speak to them or can I
No,
just do
no,
that?
just give them that.
Easy. Thanks, sir.
Thank you.
Easy to say. Sorry? Alright, now, at this point, what are we trying to do? Like, so far you've just been following along because I've been dragging you with me, right? What I'm trying to find is the amplitude has changed. How has it changed? You already have an educated guess as to how it's changed. And how has the phase changed? What angle have I been moved across by? Okay. So there was something else I should have mentioned, which is that not only is alpha real, but r is the amplitude here. So amplitude is a positive number. Yes, that's what I'm saying. That's right. Okay, so what am I going to do with this? There are two things you can do. One thing is cheap, and it's a quick fix, which kind of gets you an answer. It's not as good. And another way is longer, but it will give you a more sure answer, okay? So I will show you the long one. I'll show you the short one later on, after you know how to do it properly, okay? So here's what I'm going to do. Equation 1, equation 2, okay? Notice, this is a set of simultaneous equations. I have two unknowns, r and alpha, and I have two equations. Perfect. That's exactly the setup I need. Here's what I'm going to do. I'm going to put them together in a kind of unusual way. You're not used to seeing this, right? And usually we would say, oh, it's a bad idea to square things because you add solutions and so on, okay? But in this particular case, watch what happens, okay? 1 squared, right? On the left-hand side, I'll have r squared cos squared alpha, yeah? On the right-hand side, I'll have 1 squared, which is 1. What happens to equation 2? It's going to become r squared sine squared alpha. What happens to the right-hand side? It becomes 1. Okay. So now here, I've got a cos squared plus sine squared. So when I factor out r squared out the front, I'm left with cos squared plus sine squared, which is 1. Which is 2 on the right-hand side. So remember, because I said r is positive, that r is the square root of 2, which is exactly what you were expecting, wasn't it? So, I have an amplitude now. Tick. Okay? I'm not finished. I found r, right? But now I need to find out what alpha is. Okay? So, I've got to use both these equations here, and you'll see why shortly. Okay? I've got r is root 2. So I can say root 2 cos alpha equals 1 from equation 1. And I can say root 2 sine alpha is equal to 1 as well from equation 2. Right? So just rearrange just a little bit, make alpha as close to the subject as possible. I've got this, and I've got this. Okay? Now you're like, hold on a second. That's a bit redundant, wasn't it? Like usually when you have simultaneous equations, you find a solution, right? And then you just substitute that into whichever one you want, and you get an answer for the other one. Okay? Can you see why I need to put R into both equations in order to know which answer I want? Right? Yeah.
Is it because it's the intersection? Maybe.
Kind of.
It's because
Have a think about this. Let's just think about this. If I just stopped here, right, and did the top part, which is from equation 1, right? Aha. What angles does cos alpha equal 1 over root 2? And the answer is, cos is like this. Is going to be 45 and 315.
Yeah.
Quadrant 1, quadrant 4, right? So I don't know which one it is. But once I bring this guy in,
Oh, I
right?
had the same solution.
Aha, so alpha has to satisfy both of these. Cos is positive, sine is positive. What quadrant am I in? Quadrant 1. So it has to be, alpha must be 45, and only 45. Okay? Now, let me just use that as my opportunity to point out to you the cheap way, which does get taught, and it's kind of, has a shortcut, it's not that bad, but it has a big problem, and it's the problem we just solved, okay? Here, this line, this is not the only way you can put together these equations. Just like with normal simultaneous equations, you can do elimination, or you can do substitution, right? We've kind of done, I don't know what you call that, squaring, anyhow. There's another thing we can do this, okay? If you're really, really sneaky, you're like, all I need to do is eliminate one of the variables, right? Now the way we did this was we eliminated alpha, correct? No more alphas. Yep. You can eliminate r from there, can't you? Yeah.
No, you do r sine alpha over, well, do the second equation first.
Yeah. 2 divided by 1. That'll work, and it looks really elegant. Watch this. If I'm dividing this by this, what happens to the r's? Disappears, right? Then you get sine alpha and cos alpha. Tan. You get 1 over 1. And you say, sure enough, well, that's 45. Isn't it? Isn't it? Or, and here's your problem.
200.
Or 225. Okay? Now, you guys know, because you've looked at this graph, you're like, oh, yeah. Clearly, that looks like 45 to me. It is 45, okay? But you don't have information from this process that tells you which one it really is, right? Whereas this one does. You see how I've got two equations and it locks in which one I'm actually after.